Hey kids, Smith here. Gonna get sharing a page here and go over some notes on water. Chapter 15 right here. So there's the notes screen. And we want to talk about water for a few minutes here because what we have is a universal solvent. That's why water gets its own chapter. What we're doing is we're moving into a unit now on solutions. Well, in order to have solutions, obviously, we have to have water. Most of the chemistry we've done is aqueous by nature. So why water? Water is abundant, it's functional, and it dissolves well. Now, why does water dissolve things so well? Well, because water is very polar. That's the key here. The polarity of the water and the size of the molecule is what makes water so absolutely unique. So if something is ionic or solute, we're going to put something into water. In this case, we took some sodium chloride. And what happens is the hydrogen gets in the way of the sodium. You can see this happening right here. The hydrogen gets in the way of the sodium, and the oxygen gets in the way of the chlorine. Those two things repel each other, and the water splits that sodium chloride. Now, this is something to keep track of because water itself, it's polar, which means it's covalent. Ionic, NaCl, gets broken apart. So what does that tell you about the strength of the bonds? Covalent must be stronger than ionic. And that's absolutely true, that when we're sharing something, it's going to be held together much more tightly than when we're just transferring something. And that does make some pretty good sense to us. So now that's what happens with ionic things. Ionic things dissociate. What do we mean by that, dissociate? We mean it splits into ions. So in our case, our NaCl is going to split in to Na plus and Cl minus. We no longer have NaCl together, but what we have is Na ions and chloride ions, sodium ions and chloride ions. Now that's going to happen when things are ionic. But what we figured out is a lot of the stuff we deal with, it's not ionic at all. Most of it is covalent by nature. So these are molecular substances. Now, the poster child for our molecular is glucose, or sugar, C6H12O6. So how does water dissolve that? What happens and how is that different? Why are these two things different? Well, because in this case, now the glucose is covalent as well. So now you have a covalent and a covalent. The water is not going to be strong enough to break the glucose apart. Matter of fact, we're not going to break the glucose apart at all. It stays together as a molecule. And so instead of dissociating, what happens here is that molecule is going to dissolve, that the H2O is going to surround it, creating a sphere. So we're going to put H2O molecules all the way around that molecule, right there in the middle of our beaker here, our H2O surrounding it and just kind of pulling it apart. Now, it's still going to stay together. The C6H12O6, it's going to stay together, but we're going to break the crystal lattice apart so that individual glucose molecules will now be dissolved in water. And so what we have are these two cases where ionic things dissociate and covalent things dissolve. And that's going to have an effect on how they behave when they turn into solution, which will be in the next video that we talk about. Now, we've made note of some terms here, and we want to talk about those. Those are our terms of a solution, a solvent and a solute. So basically, if out here we had, this is a solution. Solutions are made up of solutes and solvents. Most of you have heard this before. The solute is what gets dissolved. It's the substance there is also less of. And our solvent gets the dissolving. It does the dissolving. It's the species that there is more of. This is not based on state of matter. You could have a solvent that isn't a liquid. You could have a solvent that's a gas. You could have a solvent that is a solid. That would be unusual. Most solvents are liquids. When these things get dissolved and or dissociated, we want to look at whether things are electrolytes. Electrolytes should have been one of your vocab terms that you guys defined. This is a substance that dissociates into ions. Electrolyte, think ions, all right? And we're going to have those ions in solution, and what makes them huge is they're going to conduct an electric current. That part is huge. That's what makes things this conducting. That's what tells us whether something is an electrolyte or not, is that it conducts an electric current. And if it conducts an electric current, it means that we're going to have an ionic substance that dissociated, not a molecular substance. So if we take sugar, throw it into water, no electrolytes, no electric current. Now, is there still current going through the water? Yes, because our water isn't absolutely pure. If our water was absolutely pure and we took absolutely pure sugar and threw it into water, it would have no effect. Okay? Now, within those electrolytes, some things are going to dissociate completely, some things are going to dissociate partially, and that's why we have these terms down below here, where we have strong, weak, and non. And so what we have when we have a strong electrolyte is something that dissociates completely. It's very ionic. Sodium chloride was our poster child for that. Then we have things that are non-electrolytes. They don't dissociate at all. That's our glucose down here. And then, of course, the world is an imperfect place. So there are things that dissociate partially. We're not going to deal with those very much here. Those are things like vinegar. Okay, weak acids. We haven't done our unit on acids. I don't expect you guys to know that. Just know your strongs and your nons. Strongs are ionic, nons are molecular. All right, that's how we're going to classify solutions for right now. And as I said, we're going to get into those properties a little bit more in our video tomorrow, in our next video. So that being said, why do we worry about water? What makes water such a unique substance? Well, water has surface tension. And this is really unusual. I think this was another one of your vocab terms. What it is the unequal pull of molecules on the surface of a liquid. Now, why is that pull unequal? We want to look at two different scenarios here. The first one is this water molecule right here in the middle that I'm highlighting yellow. That water molecule in the middle, that's being pulled equally in 6 different directions, right? It's being pulled out on the X and on the Y and on the Z. Everything's equal. So it's pulled normally there. But now, if we grab this molecule on top, I highlighted blue, that molecule doesn't have, it's on the surface, it doesn't have any other molecules up above it to be able to make that pull. And so it gets pulled in 5 directions. And by being pulled unevenly, that's going to pull the surface of that water and make a skin, a surface tension on that. And so that's one of the things that's unique to water. And why does water do that? Because it has extremely strong intermolecular forces called hydrogen bonds. All right, that is a unique property of water. Not many other molecules have that kind of surface tension. As I say, that's unique to water and created because of the intermolecular forces. Now, we can add things that can disrupt that surface tension, and we call those surfactants. And these are things like soaps. Mucus is a surfactant. These are things which interfere with the hydrogen bonding, and it decreases that surface tension. To use terms that you guys would like to say, surfactants are called wetting agents. And so you could actually, I'm afraid to even say it, wet water. You could make water wetter by adding a soap to it, a surfactant, adding something that's going to interact with those hydrogen bonds and decrease those pulls. Okay, that gets us through water and why it behaves the way it behaves. I'm Smath. I'm going to come back to you and talk about the rest of these notes on crystals.